So, since we said that when a system left itself will go towards a condition of maximum probability, we have to talk about what is probability. So, probability very simply put is number of ways of getting a particular thing divided by the total number of ways. So, let us say we are talking about probability of x. X is a particular thing, that is the thing that we talked about. Probability of getting a particular thing is number of ways getting that thing. So, this is counting number of x or number of getting x divided by total number of ways. So, again this omega denotes number of things, number of ways the all possible things can come, all possibilities are sigma. So, these all possibilities are called probability space or sample space. So, for example, so as we mentioned here is the number of ways of getting x and this is total number of ways. So, for example, we say that what is the probability of getting a 4 in a dice throw. So, here we have to see that what are the possibilities that are there in a dice 1, 2, 3, 4, 5 and 6. I have a dice to show you. Here is a dice, as you can see, and all of you probably have seen a dice, but it is interesting to see them when you talk about them. So, this is a dice which has 6 possibilities only. If you throw it, we can never get 7 or 8 or any other thing, we can only get the 6. So, this is our sample space in which we have to move around. Even if I do a million times, I am not going to get a 7 out of this. I am only going to get either 1 or 2 or 3 or 4 or 5 or 6. That is the constraint that I have. That is all possible outcome, in which what is the number of getting a 4? Only once, one time. I get only 4 only one. So, x is 4, sigma is I have mentioned here, number of ways getting 4 is only 1, number of ways getting all of them, let us say I said you get me either 1 or 2 or 4, 3 or 4 or 5 or 6, there are 6 possibilities, right. So, that is 6 and therefore, probability is as you said that is a sample space number of getting 6 and that is why the probability is 1 by 6. So, the probability of getting a 4 is 1 by 6 and notice this limit thing, that this is saying that this will not happen if you do just once. If I just throw 1 or 6 times, I may not get a 4 once. It is only happen when my sampling is much more. So, we need this limit omega this thing sigma tends to infinity, because for the outcome to follow the above probability calculation we need to try many times. So, now we are going to do that with a demo coin. A simpler than dice is a coin, right. The reason is that coin has only 2 possibilities, head and tail. So, however number of times we do, we can either get a head or get a tail, and hopefully they are equal. For example, I am saying that this is only true when they are of equal probability, that means both the sides are same weighted. If one side is heavier, then it will fall on that side and then other side will be seen. So, we are not considering that aspect. So, let us say we do this coin toss a few times and see what happens. So, ideally we should get half head and half tail. So, we are going to do 2 times, we should get 1 time head and 1 time tail, right. So, I got a tail, okay, second time I got a head and I got a tail again and I got a tail again. So, I got 3 tails and 1 head. If I do a small number of times, then I may not get the half thing. I will only get half when the number of trials becomes infinite. So, we are going to show you that how increasing the number of coin tosses will lead us to half probability, because I could do only 3 or 4 times and the statistics is only true when it is done multiple number of times, not 1 or 2 times, right. So, we are going to just exactly see that. So, what we do in computer is that we draw random numbers, just like, so we are considering these events as random. Let us say, imagine if you could push with the same force, exactly same force every time, your outcome would be deterministic. So, when you throw that, we assume that every time we are randomly pushing it, like our force is like kind of random, right. But in computer we will exactly draw random number, almost random number, like it is called pseudo random number to be more precise, but they are random for our own purposes, you can say that. So, we can define that if something is let us say we are drawing between 0 and 1 and something is below 0.5, we say that it is head, above 0.5 it is tail. So, we are totally defining a random number and drawing head and tail, and we can do as many number of times as we want, and we will show that probability of getting head is what, as a function of number of trials. So, you see this is a program that is written in Python. We are going to run the program and it is asking that enter the number of games you want to play. Okay. We say we want to play only 10. And what we see here, that the probability of obtaining head is increasing. First it was 0, so there was no head, and then increasing to 1 and then slowly coming down, again it is increasing and then coming down. So, it is really fluctuating. So, our probabilities are not really half or 0.5 with these few trials. Let us do some more time, let us do up to 100, and you see it is still 0.5 is somewhere here, it is still not there yet, still fluctuating. So, let us do now 10,000 times, and you see that the probabilities has converged to a value of 0.5. You can see that, right. So, this is the 0.5 value and it has converged to 0.5 after oscillating above and below 0.5. So, you see this is called law of large number. We have done only 10,000 times, we have not done 10 to the power 23 times, 10,000, then 10 to the power 23 is almost like million, billion, billion. Billion is 9, right, 9, 9, 18, 18 plus 6 is 10 to the power 24. So, it will be almost like 10 to the power 24. So, million, billion, billion times if we do, you can imagine that how almost accurate that probability will come to, and that is the number that we deal with when we talk about a glass of water or a cylinder of gas. We do not talk about like 10,000 particles. Of course, we do simulations with 1000 to 10,000 particles and still it comes out to be okay. So, similarly, let us do die throw. So, now you know that there are 6 possibilities and each of them has 1 by 6 probability, like 1, 2, 3, 4, 5, 6. If we throw the dice, let us say for 10 times or 50 times, do you think we will get the probabilities of each of them as exactly 1 by 6? We are going to do that the same way as we have done the coin toss using our computer program. However, in this case we have all the 6 possibilities. We can again draw a random number between 1 and 6, an integer random number, and we can define each of them as 1, 2, 3, 4, 5, 6, and we can calculate the statistics of it, and that is what we are going to show you in our Python program, because we are not really want to throw a die a million times, it will take time, and secondly we have powerful computer programming tools available in order to achieve the same task in a very short time. So, we are going to do that. See, this is again a very small simple Python program, and I am running the program. It is asking me number of trials. So, I give 6 trials, because 6 trials are only required to get all of them as 1 by 6, right. So, I give 6 trials, and what do I get? I get 2 times 1, as you can see here. I get 2 times 1, I get 0 times 2. So, in my 6 trials there was no 2, I get only 1 times 3, and I get only 1 times 4, 1 times 5, 1 times 6. So, although these probabilities came fine, which is supposed to be 0.167, this and this did not come correctly. Let us then increase it and make it 100 times, and what do I get? Again, as you can see, none of the probabilities came out to be right, because in 100 times I should have got around 16 point some times, 16 17 times, right. And you can see number of occurrence of 1 only 8, much less than expected. 2 17, very close to what we expect, and then 3 4 5 and 6, all of them came little bit larger, little more than the number, right, because we did only 100 times. Now, let us do 10,000 times. 10,000 times is a ballpark number, by the way, we can do more than that, and these are the outcomes that we got. As you can see, 1 5 2, these are the outcomes that we got, and at the end of our outcome we will have the probabilities which is mentioned here. Now, you see most of the probabilities are very close to 0.167, 0.169, 0.170 and things like that. Now, if you want to be more accurate, so this is nothing but 10,000 times, right. If I want to be more accurate, let us do 100,000 times. This was too fast, and let us see what we got at the end of the program. I can pull it down. Now, you see with 100,000 we got up to second decimal place correctly, 0.166, 167, 167, 168, 165 and 0.167. So, now we see that only by 100,000, 100,000 is nothing but 10 to the power 5 only. We have not reached even a billion thing, we have to go to million, billion, billion, and you can imagine how accurate those probabilities will be when we talk about molecules, molecular systems. Okay. So, this is to show you that the statistics will work right when we deal with atoms and molecules for representing a bulk system. It will work out right, because it is even working with just 100,000 trial runs, but it did not when we had very small number 1. So, it will be very helpful later on to think that whenever we have doubt on the statistics, you imagine that law of large number will play a big role in determining that what will be the outcome of the event. Now, we will switch back to little bit more probability calculations. So, we have just saw simple events meaning either getting 1, 2 and things like that out of a die, or head and tail out of a coin throw. Now, we can combine and show that how AND probability multiplies. Remember, I told you about multiplication of the microstate just now. We said that if I have W microstate for one system and W for the other system, then the combined system will have W into W, which is W square. Where does it come from? We will be clear here. So, what is the probability of getting a 4 in the first throw, and look at this AND, I am talking about AND probability, isn't it? Here also there is an AND here. So, what is the probability of getting 4 in the first throw and a 6 in the second throw? It is probability of getting x and y is p x and multiplied by Py. However, again we are assuming that these are independent events. That means getting a 4 in the first throw does not affect anyway the next outcome of the die throw. They are all independent, just like coin throw. So, we know the probability of x, right, that is 1 by 6, and the probability of y also is 1 by 6, therefore, probability is 1 by 36. So, similarly, what is the probability of getting 2 heads in a row? Half into half, 1 by 4, 3 heads in a row, half into half into half. So, what is the probability I will get 10 heads in a row? So, that means first toss 10 and second toss 10 and first toss head and second toss head and third toss head and fourth toss head and fifth toss head, like that up to 10th toss, it will be 1 by 2 to the power 10. So, and probability is multiplied. So, that is why what is the probability of getting W microstate for a system and W microstate for the second system is W into W. Okay. So, that is why we had the W square. Now, what is the probability that we will get a 6 3 times in a row? As I said, it will be 1 by 6 to the power 3. What if the probability is not independent? So, if the probabilities are not independent, then the first outcome will affect the second one. However, and will still multiply, and will multiply. However, it will not be the same value. It will not be 1 by 6 like what you have for the dice throw. We will give an example. What is the probability that drawing from a deck of cards we get 2 hearts in a row? Now, we know that if you know about the cards, there are total 52 cards, out of which there are 13 hearts. Okay. So, what is the probability that we will get 2 hearts in a row? So, we have to get the first heart. What is the probability? It will be 13 by 52. For the second heart, I can only select out of 51 card, because there is only 51 card left and there is only 12 hearts left. So, it will be that. So, as I said, 13 by 52 multiplied by 12 by 51 giving us 156 by 2652. So, here the probabilities are not independent. However, the multiplication came because we wanted an AND condition. So, as I said here, probabilities multiplied, but both probabilities were not equal. Now, let us talk about OR probability. OR probability adds. What is the probability of getting a 4 or 6? See, we want 4 or 6, either of them it is okay for us, 4 or 6 in the following, in the throwing of a dice. So, we put that this sign as an OR sign. So, x is getting a 4 and y is getting a 6. So, we say x or y will be added up, p x plus p y, 1 by 6 plus 1 by 6 is 2 by 6, and you can understand why, because you let us say you are in your sample space, you have 1, 2, 3, 4, 5 and 6. You want either 4 or 6, whichever is fine with you. So, if you throw, you get a 4, or if you get a 6, it is okay for you. So, which means that we have to add up those probabilities, because now this is 2 out of 3 that we are 2 out of 6 that we are talking about, and that came because each of them has 1 by 6 1 by 6 probability. So, what is the probability that we get 1 or 2 or 3 or 4 or 5 or 6? 1, because we will get either one of them. So, what is the probability of tossing 2 coins, that in the tossing of 2 coins either the first one or the second one will be head? See, here also there is an or here, either the first one. So, we know tossing of a 2 coin, what will happen, what are the possibilities, HH, HT, TH and TT, these are all 4 possibilities total. So, I am saying that what is the probability of tossing 2 coins, in tossing 2 coins, the first one or the second one. So, first one comes head 2 times, second one comes head 1 time. So, there are 3 out of 4 possibilities. How do I get that? We can get that exactly here. So, these 2 and this one all belong to the condition above. So, we say that p x or y. So, p x has a possibility 2 by 4, p y, which means that head comes later, has only one possibility. So, it is 1 by 4 giving us 3 by 4. So, I can do both the ways, you see. So, I calculated the individual possibilities, or I count the all possibilities like I did in this case. I counted that in order to satisfy this above condition, how many such events are there. So, I am giving a different name for that. Let us say I am saying that it is p x prime. P x prime is either first one or second one. So, there I do not have to add up, I straight away calculate that it is 3 and out of 4 possibilities, or I break that into 2 individual events. In one event I say that first one is head, another event I say that second one is head, and I add those 2 events probability, and I get this particular thing. Is this part clear? Okay. So, now combining AND and OR, that is slightly more complicated. Throw 2 normal 6-sided dice, what is the probability of rolling a 8 as the outcome of each dice? Now, you see, as I said that with one dice we cannot get 8. However, if we throw 2 dice and calculate the sum of the outcome, then we can get anywhere from 2 to 12. Why 2? Because the smallest number is 1. So, 2 dice, 1 plus 1 will be 2. So, minimum it has to be 2. What is the maximum? Say both of them come 6, 6 plus 6 12. So, it can be anywhere between 2 and 12. Now, in that I am asking, so what are the outcomes that is possible for 2 die throw? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, is any of these possibilities are there, and I am asking what is the probability of getting 8. Now, here you see you cannot simply do 8 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 8 by 11 you cannot do. Why? Because there are more number of ways of getting that. This is only possible if 2 dice are indistinguishable. You do not care about throwing 2 die and all, you just happen to place those dice, but here we are talking about first die versus second die, first dice versus second die. So, therefore, they are distinguishable dice, and we have to see that how many possible ways we can get the 8. So, we can do these 2 ways. One way is by calculating all possibilities, which means that number of ways to roll a 8 is either we roll 2 6, that means first die is 2 and second die is 6, or we roll 3 5, or we roll 4 4, or we roll 5 3, or we roll 6 2. We roll any of these 5 will get an 8. So, we know all 5 ways of getting a 8, and what is the total number of outcome? Total number of outcome is that my first dice can be any of these 6 and my second die can be any of these 6. So, which means I can take 1 from here and 1 from there, I can take 1 from here, 2 from there, 1 from here, 3 from there, 1 from here, 4 from there, 1 from here, 5 from there, and 1 from here, 6 from there. So, for 1 I have 6 possibilities, for 2 also I have 6 possibilities, for 3 also I have 6 possibilities. So, for 6 of them I have 6 possibilities, each of them I have 6 possibilities. So, 6 into 6 total 36 possibilities are there. You imagine that you throw a die and you get any of these possibilities, you throw the second die and you get any of these possibilities. So, total possibilities of outcome will be 36, out of which only 5 will give you 8 as we mentioned here. So, we get 5 by 36, but we now going to use and or ways of doing it. That is the first way is done. Now, second way, by combining the individual probabilities or probabilities. So, what do you say that 8 can be obtained from either 2 or 6 or 3 or 5. See, I am saying or 4 or 4 or 5 and 3 or 6 and 2, I am saying or. So, I am adding up, but when I talk about 2 and 6, then I am saying that this is P 2 multiplied by P 6, because I need 2 and 6 in order to get 8. So, that is an AND probability for each of them, whereas between of them that is OR probability. Now, we know 2 6 how many ways you can get, 1 by 36 ways, right, because 1 by 6 into 1 by 6. So, each of them in turn are AND probability, and how much you get. So, I have given the example for that. So, therefore, I can write P 8 as 1 by 6 into 1 by 6 giving us 2 6, this is P 2 6, this is P 3 5, this is P 4 4, this is P 5 3, this is P 6 2. Is it clear? So, now combining all that, we are also getting the same as 5 by 36. So, this is just a way to show that how to calculate the N and all probabilities, how to calculate in general the probabilities of multiple events, which will be definitely useful in later on when we will talk about the microstates and then distributions and arrangements and calculation of their probabilities. As we have seen very just now itself, that we talked about multiplication, we talked about microstates of two different systems. So, when you combine those microstates of two different systems, it is like, what is the number of microstates for a dice? 6. What is the microstate for another dice? 6. Now, what is the number of microstates for 2 dice? 36, because 6 possible ways of getting this, 6 possible of getting this. When you combine that, it will become 6 into 6 is 36. So, microstates are multiplicative, entropies are additive, and that is why the ln function came. So, I am just reiterating whatever I said before after giving you this example. Okay. So, now again we will coming back to the same question, that is this 5 by 36 will you observe in 1 or 2 dice or not. So, the thing is that if we really calculate the probabilities of getting a 2, how many possible ways we can get it? How many possible ways we can get the 2? Only one possible ways, that is correct. How many possible ways you can get 3? So, I will write the possibilities here, 1 1, that gives us 2. How many possible ways you can get 3? 1 2 can give me 3, or 2 1 can give me 3. So, 2 possible ways. How many possible ways you can get 4? 1 3 will give me 4, 2 2 3 1. 3 possible ways. How many possible ways you can get 5? 1 4, 2 3, 3 2, 1 4, 2 3, 3 2, and anything else? 4 1. That is 4 by 36. So, we see only 4 possibilities. How many possibilities you can get? 6. 1 5, 2 4, 3 3, 4 2, 5 1. 5 possibilities. How many ways you can get? 6 7. We will see it is 6 possibilities. I will not do that, and you can do that again. This is 5 possibilities. I will just remove this side, and 9 will be 4, 10 will be 3, 11 will be 2, and 12 will be again only one way. So, now if I plot it, that probability, I will plot it, I will get this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, approximately I am plotting it. So, the peak will be maximum for 7. I will just do this once more. It will be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, this is for 6 having maximum probability of like 6 times it will occur. So, 6 by 36 is 1 by 6.167, it will be the maximum probability, it is symmetric around that. So, this is typically called probability mass function, probability mass function, in which we count the probability of all possible events. So, what is the most probable situation? 7. So, that means if you roll it many times, you are going to see 7 as an outcome which is more in number than 2. okay, and we are going to do the experiment here to show you exactly that. So, this is again a program that is there, and let us run the program and put how many trials we need, at least 10-12 trials we need, right. So, let us do it for 50, just 50. So, it gave us the probability of 2, 3, 4, 5, 6 the occurrences it gave. So, probability will be just these occurrences divided by 50, okay, and these probabilities are plotted here. Does it look like the one that I have drawn just now? Does it look like the one that I show here? Does it look like the one that I am showing here? No, right, because we have done only 50 times. Let us now do much more than that. Shall I do 1000 times? Okay, do 1000 times. It is beginning to look like that, beginning 1000 times. So, let us do there are how many 11 outcomes, right, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, no 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yeah, there are 11 outcomes, right. So, let us do 11,000, so that we expect somewhat once more. Yep, I ran the program now, and let us calculate the probability. I will reduce a little bit and then I will increase it. And you see the number of occurrences has been given here, and as you can see the 7 now has become maximum, and if you want to calculate the probability of that, I can calculate that. So, 7 has come 1910 times, 1910 divided by 11,000 is 0.173. We are expecting 0.167. So, although it becomes symmetric, it is still not perfect yet. Okay. So, let us and what is the probability of 2 is 1 by 36. So, let us see 308 divided by 11,000 is 0.028, and 1 by 36 means 0.0277 means 0.028. So, 2 has come correctly, but not the 7. So, in order to get that, we have to run some more time. So, instead of 11,000 I will put 100,000, just like we did before, and I got that 100,000 result. And if I go down, I can show you the values. So, 7 came 16,883 out of 100,000. So, what is the probability? 0.168. We are expecting 0.167, is accurate up to almost third decimal place. No. So, if I do instead of 100,000 1 million, we are going to get more accurate result, and as you can see it is already very symmetric looking distributions. So, again law of large number took hold, and we are getting the desired outcome from the throw of 2 die as the way expected. But only thing you remember that this one is we can call as most probable distribution. So, all those distributions, that means getting 2 all that has some probability, right, but getting a 7 is most probable, right. So, that is what we got from this particular exercise. Now, let us say do one more and all probabilities combined. So, what is the probability that exactly one of the 2 top cards of a standard well shuffled deck of cards is a heart. So, now we are not saying that both of them have to be heart, we are saying one of the 2. Now, when you say one of the 2, I can do how many ways. So, if my first card is a heart, the second should not be a heart. My first card can be heart by how many ways? 13 by 52 ways, and second card should not be a heart. So, now there is no how many cards are not heart? 39. So, 39 by 51 is one way of getting it. I have to use OR probability. So, my first card should be a heart, second card should not be a heart, or I can say my first card should not be heart and second card should be a heart. So, first card should not be a heart is 39 by 52, second card should be heart is 13 by 51. Now, addition of that will give us the desired number, that exactly one card out of the two. So, I have done that. The first is a heart, second is not a heart. Why is first is not a heart, second is a heart. Now, I have x and y and I can combine that any of these, either of these two events will give me the desired result is addition of the two, and that is giving us this. We can also say that using a NOT probability. What is a NOT probability? That I want either of the cards should be heart, right. So, I want exactly one out of the two cards should be heart. So, I can say that what is the probability that I get either both of them as hearts or none of them as hearts. If I subtract these two probabilities, then I will get either of them as a heart. You understand? So, to calculate the probability of both of them having a heart. So, what is the probability that neither? Okay, and that way also we can get that. Okay, so you understand. So, exactly one of them should be heart. So, if I get two of them heart, it is not helping. If I get none of them a heart, it is not helping. So, if I subtract that probability, there is only one possibility remains, that is either one of them or exactly one of them is a heart. Now, second one, if I say what is the probability that neither of the two cards is a heart, neither of the two cards, which means again I can do it in two different ways. I can say that first card is not a heart is 39 by 51 ways, second card is not a heart, sorry 52 ways, second card is not a heart by 38 by 51 ways, because there are 39 non hearts. So, I am picking any of them, then I am left with 38 non hearts out of 51 cards. So, I am picking third. So, this is the probability that neither of the two cards is a heart. Okay. But I can do now again with a NOT probability that neither of the two cards is a heart. I can say that 1 minus either one card is a heart or both card is a heart. So, this is the first one that I did. Second one, both card is a heart or any one card is a heart. So, any one card is a heart we have got already on the top, right, and both card is a heart also we have calculated before. So, when we subtract that we get the same number as before. So, what I am saying is that there are different approaches to get the probabilities. Once you think about the event in mind, then you will be able to get to that. And now that we know the probabilities, we are going to see that what will be the probabilities in certain distributions, meaning when we distribute let us say distribute some chocolates to people, or we distribute some balls to some holes, or we distribute some energy to particles. What kind of possibilities will arise and what will be the probabilities of each of those possibilities? Again, our aim is to find out which possibilities are more probable. Just like we saw the two dice throw, the probability of or the possibilities of getting 2 and possibility of getting sum as 7 is more probable. Similarly, when you distribute the thing, we will see which is more probable and which is not.